Hello everyone, this is a presentation of gases intended for Chemistry 1. I'm going to take you through the background of our understanding of gases, as well as walking you through a couple of very important gas laws and some calculations that we could do with those. Our understanding of gases is based on something called kinetic molecular theory, which the details of that aren't hugely important, but you ought to have some background, so I'm going to take a couple of minutes to go through that first. So first of all, we have to remember that all matter is made up of a bunch of very small particles called atoms and molecules, and that these particles are moving at the atomic level. If they are moving enough, if they have enough kinetic energy, then the particles are moving unimpeded by intermolecular forces. So in other words, they're not sticking together any longer. So there are 5 tenets to kinetic molecular theory, and here's the first of them. It's important to recognize that gases are made of matter. Because they are matter, this means that the gas particles have both mass and volume, as all matter does. The second tenet of kinetic molecular theory is that although, yes, they do have volume, the spaces between the gas molecules are much, much larger than the actual gas particles themselves. This means that gases are mostly empty space. They are mostly vacuum. The third tenet of kinetic molecular theory tells us that gas particles are in constant random motion. The presence of one gas particle does not affect the motion of any others, and this really sets them apart from solids and liquids. In solids and in liquids, the particles all affect each other. In gases, they don't. We are assuming, therefore, that the intermolecular forces in gases are negligible. The fourth tenet of kinetic molecular theory is that the collisions of gas particles with the walls of the container that they're in are observed as pressure. Now, container is a very general sense here. It's whatever the gas is in. That could be something rigid like a jar. That could be something flexible like our lungs. That could be something a lot less defined like the gravity of the Earth. But regardless, whatever is bounding that gas in as the gas collides with it, that is what we observe as pressure. Pressure is going to get a whole separate discussion of its own. Understanding what gas pressure really is and what it is measuring is vital, but those picky details aren't really necessary for today. The fifth and final tenet of kinetic molecular theory is that the average kinetic energy of a gas sample is proportional to its temperature in Kelvin. And it is very, very important that we keep that in Kelvin. This does not work for Celsius or Fahrenheit. Okay, again, temperature must be in Kelvin. And as a reminder, to convert from Celsius to Kelvin, we're going to add 273 degrees. So the tenets of kinetic molecular theory are going to let us make some substantial predictions. We're going to be able to relate a number of macroscopic or real-world size properties of gases to one another based on these premises. This is something we cannot do for liquids and solids, so this is very different. All right, the first pair of quantities that we're going to relate are quantity itself and volume, which this makes sense. The more gas that we have, the larger a space that that gas is going to occupy, as long as we keep everything else the same. And this is definitely something you've observed in real life before. The more gas you put in a balloon, the bigger the balloon will be. And as we let gas molecules out of the balloon, if we keep everything else the same, the balloon is going to shrink. So we've got nothing new there. But that idea is actually captured in something called Avogadro's law. As obvious as it seems, the quantity of gas is directly proportional to the volume of that gas. But there's a very important subtlety here. And that is that you may notice the identity of the gas isn't involved in this law. It doesn't matter what the gas is. It doesn't matter if we're talking a mixture of gases. It doesn't matter if we're talking a blend of gases. It could be 30 different gases. It doesn't matter. It's going to turn out that all gases behave exactly the same, no matter their identity. So it doesn't matter what kind of gas it is. The volume is directly proportional to the amount of gas present. Directly proportional to the point where if we have 2 containers at otherwise identical temperatures and one of them is twice the volume of the other, we can immediately conclude it must contain twice as many gas molecules. twice as many moles, same thing. All right, we're not going to do a whole lot with Avogadro's law in depth at this point, but these next three combinations we are. The first of those is volume and temperature. So we are going to find for a sample of gas, when the amount of gas and the pressure of that gas are held constant, volume and temperature are directly proportional to one another. Now this is another thing that you've undoubtedly observed before in your lives. Go to a children's birthday party in the middle of winter, and you take a balloon that was filled at room temperature, and you take it outside on a very cold winter's day. You're going to watch that balloon shrink. It's going to get a lot smaller. The amount of gas in the balloon did not change, but because the particles now have so much less kinetic energy, they're occupying a much smaller volume than they were previously. This concept is known as Charles's law. The name of the law isn't very important, but how to use the law definitely is. Charles's law says as the kinetic energy of the gas increases, a fixed sample of gas will expand at constant pressure. We can write this law using the following equation. V1 over T1 equals V2 over T2, where V1 is the first volume at the same time as we're measuring the first temperature, that's T1, and then V2 is the second volume at the same time we're measuring the second temperature, which is T2. Good time to remind everybody the temperatures have got to be in Kelvin. If we go back here, we see that if this temperature is 0, this math blows up. And of course, here in New England, we have experienced 0 degrees Celsius plenty of times. But on 0 degrees Celsius days, the laws of physics don't stop. So we have to be in Kelvin, okay? Incidentally, as an aside, Charles's law is actually exactly how we derived the value of absolute zero. Since volume and temperature are directly proportional, this law can be used to figure out at what temperature the volume of a gas would be zero. And if you're with me in AP next year, we will do a lab where we do exactly that. By taking data of temperature and volume proportions at a number of different temperatures, we can extrapolate to the temperature for zero volume. Let's do a couple of sample questions with Charles's law. So sample problem number 1. Supposing we have a sealed sample of gas at 25 degrees Celsius that has a volume of 6.45 liters, we want to know what volume will that same sample of gas have at 98 degrees Celsius, assuming pressure is constant. Now some notes about this problem. That word sealed tells us that the quantity of gas is constant. That's important because that's one of the conditions of Charles's law. If moles and pressure weren't constant, we couldn't use Charles's law. And then they flat out told us that pressure is constant, so we don't have to wonder there. Also, another reminder that I will remind again and again and again, we must convert temperature to Kelvin. So to solve this problem through, we're going to take our V1 over T1 equals V2 over T2 equation and simply plug in the values that we've got, again being certain to convert Celsius into Kelvin. So for V1, we have 6.45 liters over T1, 25 degrees Celsius converts to 298 Kelvin, equals X, our unknown, the second volume, over T2, 371 Kelvin. And then we multiply through, and when we do so, we find that our new volume would be 8.03 liters. Here's a second sample Charles's law problem. So supposing we take that same starting gas that we had before, a 6.45 liter sample at 25 degrees Celsius, we could ask at what temperature will that gas have a particular volume. So this time we want to know what temperature are we going to have to raise it to have a volume of 15.7 liters. A reminder once again, our temperatures have to be in Kelvin. So we once again populate this into Charles's law. We have our 6.45 liters over 298 Kelvin. That's 25 degrees Celsius converted to Kelvin. And we're going to set that equal to 15.7 liters over our unknown temperature. When we solve that through, we find our unknown temperature is 725 Kelvin. We could leave it at that if we wanted to, or we could convert that to Celsius by subtracting 273 degrees. As long as you are clear about the units, it doesn't matter which units you use. Okay, moving on to the next relationship. That is pressure and temperature. we're going to find that pressure and temperature of a given sample of gas are also directly related when quantity and volume are held constant. So for volume to be constant, we need a rigid container. Picture a gas of any kind in a rigid container, like, for example, the carbon dioxide that you find in a can of soda. If you heat the can of soda, the pressure of gas is going to increase, and if you heat it too much, you will actually heat it to the point where the can bursts. Okay, so pressure and temperature are directly related to one another. And this is known as something called Guy-Lussac's law. Once again, the name of the law isn't important, but putting the law to use is. Guy-Lussac's law says as the kinetic energy of the gas increases, the particles of gas will collide with their container more often if the volume is fixed. And a fixed volume is usually going to be indicated by calling it a rigid container or naming a material that is rigid, like steel or glass. Those are both absolutely rigid containers. Those are fixed volumes. Guy-Lussac's law can be written as P1 over T1 equals P2 over T2, where this time P1 is the first pressure measured at the same time as the first temperature, and P2 is the second pressure measured at the same time as the second temperature. It is not coincidence that this is taking exactly the same form as Charles's law did. These two laws are very similar. Once again, a reminder, you must use Kelvin. Kelvin is necessary. Another way of writing that would be that Guy-Lussac's law, pressure over temperature is constant. If we had a pressure of 0, that would naturally correspond to 0 collisions with the container. The gas is only going to have no collisions whatsoever if it stopped moving, which it would do only at absolute 0. Let's take a look at a sample Guy-Lussac's law problem. If we have a sealed sample of gas at 54 degrees Celsius in a rigid container that has a pressure of 1.36 atmospheres, what pressure will that same sample of gas have at negative 15 degrees Celsius? So a couple of notes about this question. Once again, that word sealed tells us that the number of moles are constant. Rigid tells us that the volume is constant. Again, anytime we have a rigid container, that's something like steel or glass, it's not flexible, it's not changing. And a reminder, yet again, we must convert temperature into Kelvin. So we take our details here, we take our 54 degrees Celsius, convert that to 327 Kelvin, that's our T1, 1.36 atmospheres, that is our initial pressure. Converting negative 15 degrees Celsius to Kelvin, that gives us 258, and we are putting our final pressure as the unknown. So to solve this through, we would have 1.36 atmospheres times 258 Kelvin divided by 327 Kelvin gets us a final pressure of 1.07 atmospheres. Sample Guy-Lussac's law problem number 2. A sealed sample of gas at 54 degrees Celsius in a rigid container has a pressure of 1.36 atmospheres, so we're starting with the same starting condition once again. If the container will burst if the pressure reaches 4.28 atmospheres, at what temperature will the container burst? So we are going to solve for the temperature at which the pressure becomes high enough that the container is going to burst. And yet again, temperature must be Kelvin. This is once again a matter of populating in values into Guy-Lussac's law. This time it is the second temperature that is our unknown. So we are going to take 1.36 atmospheres over 327 Kelvin equals 4.28 atmospheres over our unknown final temperature. And when we solve for x, we find it is 1029 Kelvin, which again we could convert to Celsius, but that isn't necessary. You can leave it as Kelvin so long as you make sure that you are clearly indicating it is Kelvin. All right, our final combination of properties we are going to compare are volume and pressure. Volume and pressure are inversely related when quantity and temperature are held constant. If the kinetic energy of the gas is held constant, the number of collisions with the container are going to depend inversely on the size of the container. If you picture squeezing a balloon, the more you squeeze the balloon, the higher the pressure inside the gas becomes, because the particles have less room to move around, so they're colliding with the container more often. We can express this in Boyle's law as a mathematical equation. Pressure times volume equals constant. If we have two identical sized samples of gas at the same temperature, the same quantity of gas that is, the gas in the smaller container is hitting the walls more often, so the pressure is higher. And the gas in the larger container is going to hit the walls less often, so the pressure is lower. Boyle's law can be written as P1 times V1 equals P2 times V2. And I caution you to watch out, this is an inverse relationship, so this is different from Guy-Lussac's law and from Charles's law. Pressure and volume are inversely related to one another. So in this law, P1 is the first pressure measured at the same time as the first volume. P2 is the second pressure measured at the same time as the second volume. So let's do a couple of sample problems with Boyle's law. If we have a sealed sample of gas at constant temperature that has an initial pressure of 0.050 atmospheres and an initial volume of 0.720 liters, what pressure will it have at a volume of 0.020 liters? Some notes here. Sealed tells us that the moles are constant. This time we don't have to worry about Kelvin because there is no temperature. So long as the temperature is constant, this is going to apply. So once again, this is simply a matter of taking the values that we've got and plugging them into Boyle's law. Our initial pressure, P1, was 0.050 atmospheres. Our initial volume, V1, 0.720 liters. Our final pressure is what we are solving for, so we leave that as our unknown x, and our final volume is 0.020 liters. X in this case, when we solve the math through, is 1.8 atmospheres. So we see that by reducing the volume by quite a lot, we are raising the pressure by quite a lot, which Boyle's law tells us was going to happen. All right, and our final sample problem here today. If a sealed sample of gas at a constant temperature has an initial volume of 3.65 liters, what was its initial pressure if it has a final pressure of 5.61 atmospheres at a volume of 0.875 liters? So once again, sealed is telling us that the moles are constant. In Chem 1, the moles are always going to be constant, but if you're with me in AP, that won't be true. This time we're going to use the final conditions, our V2 and P2 conditions, to calculate the initial pressure. So we take Boyle's law. We are going to input x, unknown, for our initial pressure, because that's what we're trying to find. We're going to input the initial volume of 3.65 liters, our final pressure of 5.61 atmospheres, and our final volume of 0.875 liters. And when we calculate this through, we find that our initial pressure had to be 1.34 atmospheres. The typical challenge with these gas law problems is not using any particular gas law. It is determining which of the gas laws it is that you need to use. That's the thing to be careful for here. If you have any questions, you can please email me. Have a great day.